So in this our last hour, we will study the Thomson scattering and radiative reaction force, which will be used for the oscillating systems as well. Now, basically, first we will study the scattering of the electromagnetic waves from electrons, free electrons, not bounded electrons. Basically, what will happen? We know what will happen. We see in the when we studied that the radiation. So, incident electromagnetic wave will oscillate the free electron, and oscillating electron will accelerate and it will radiate. So basically, we will have a tool, electric field due to the acceleration of charged particle, and this is non-relativistic. So the non-relativistic form of the field, electric field of the accelerated charged particle is this. You can calculate the Poynting vector, c over 4 pi E cross B. This is in Gaussian units. And B is n cross E. B, E, and n are mutually orthogonal to each other. So let's say these are the fields of the accelerating charged particle, and this equation turns to be c over 4 pi square of the acceleration along n. N is the propagation direction. And we know that the power emitted per Salt angle is S dot n times the r square, because the dp over the Salt angle times the r square is the area element. So if you take the r square over here, that becomes power emitted per Salt angle. But generally, incident wave will have some polarization, and you can take this into information to the definition of the power emitted per Salt angle in the following form. So you can take the projection of the electric field towards the polarization. So we put a star. Star denotes that epsilon in general is a complex number that could be linear, circular, elliptical polarization, or unpolarized. But we need a polarization vector, unit vector, times the r. R is the point from the emitted radiation to the point of interest, and the square. So basically, if we have a polarization, we have to take the projection of the field along the polarization unit vector. And if you take the electric field and plug in there, then you will obtain a formula c over 4 pi r epsilon complex conjugate dot the electric field over there, that is E over C n cross beta dot, that is V dot over C over R, and take the absolute square. As you see that this will be cancelled out, and we will obtain for the power emitted per Salt angle to the following form. So take the E and C and write the beta as V dot over C. So this is C to the 4, cancels one of the C, and that will be E square over 4 pi over C cube. So the rest epsilon complex conjugate dot n cross acceleration square. And if you open this is equal to, this term is equal to what? N dot v dot along n minus n dot n along v dot square, and you are multiplying, taking the scalar product with the epsilon complex conjugate. And if you do this, what you are going to obtain? So let us go one more step. This will be n dot acceleration epsilon complex conjugate dot n, and this is 1, n dot n is 1, epsilon complex conjugate dot v dot square. And we know that the n is the propagation direction of the scattered, not a scattered, yes, not in general, n is the propagation direction of the wave, and epsilon complex conjugate is the polarization. So polarization is orthogonal to the propagation direction. Therefore, this term will be 0 because epsilon is perpendicular to n hat. So power emitted per Salt angle for an accelerated charge will be the following: E square over 4 pi over c cube epsilon complex conjugate dot acceleration. So if there's a polarization, the power emitted per Salt angle will be in that form. So basically n is the propagation direction, and epsilon hat is a unit vector orthogonal to the propagation. So let us back to the scattering of the electromagnetic waves from the electrons. Basically, we are working in low frequency. The energy of the electromagnetic wave is less, or in other words, the momentum of the electromagnetic wave is not important relative to the mass times speed of light, mc, of the electron. So the momentum of the electron is less than mc. So if it is high, then we have to worry about the momentum conservation, and that scattering will be the Compton scattering. But now we are working in Thomson scattering. In the Thomson scattering, there is no transfer of the momentum between the electron and incoming electromagnetic wave. So basically, electric field component of the incoming electromagnetic wave has some polarization. That will be this polarization in our calculation. It has some oscillating amplitude and propagating at k0. So if you multiply with the charge, that will be the force, and the force is equal to mass times acceleration. Therefore, you can write that the acceleration of the oscillating charge when interact with the electromagnetic wave, that will be some polarization along the direction of the oscillating electromagnetic wave, and multiply by E, divide by mass, so that will be E over m. E0 is the amplitude of the oscillation, I k0 dot x minus I omega t. So actually, if the electromagnetic wave interacts with the charge, free charge, that this will be the acceleration of the charge. So the charge will oscillate along the polarization direction of the incident wave. And we have the nice formula for the power emitted per Salt angle for accelerating charged particle. If it has the polarization, it is the form is this. So we derive this, and let us take this information and plug in and try to find the scattering cross section per Salt angle of the electromagnetic wave through the electrons. So basically, this is pretty simple. We have power emitted per Salt angle at any instant, but as you see that the field is oscillating at frequency omega, and therefore the acceleration is oscillating at frequency omega, we have to take the 1 cycle average of this. So if you take the 1 cycle average of this quantity, then you will deal with the square of this term. So basically that will be the cosine square if you take the real part, and the cosine square omega t for 1 cycle oscillation is 1/2. So basically in the calculation we will have the following. So let us write the form. C over 8 pi. I will discuss the terms one by one. And square of the E0 square. So E0 square, this one. And square of E square M square. Divide to the C to the 4th and multiply by the C, that makes C cubed. So let me write the result and you will see that what is going on. E square over MC square of square, and the rest over term will be the scalar product with the polarization after the scattering, that the polarization before the scattering. You are familiar this formula when we studied the radiation. We all the times deal with the scattering, the polarization before the scattering, after the scattering. So let us look at the units. We have E square, C to the 4th times C, that is C cubed. And what else? We have square of M square. Yes, we have the M, and to take the square is that will be the M square. And okay, we have E square, E to the 4th. Okay, we have M square because the square of this will be M square. And we have what? C cubed, and that is C to the 4th times C. And we have 4, and here we have the 8 because 4 is multiplied by 2. If you integrate through the 1 cycle, if you take the time average for the 1 cycle, you will end up 2 factor extra. So this is the situation. And why we write this, we see something interesting here. This piece is the energy density, so energy per volume. If you multiply with the speed of light, what you are going to obtain is a unit-wise energy per volume times length per second makes energy per second per area. That will be corresponds to the incident energy flux. So basically, this whole stuff here can be called incident power per area. And if you take this to the other side, you can deal with the definition of this goes up, power is a dimensionally cancel. This will be the area per Salt angle. That corresponds to scattering cross section per unit Salt angle. So the definition is the following. So let us write to the left hand side. That is energy radiated unit time, unit salt angle, this is the energy radiated per unit time per unit salt angle, this term, divided by this, that is the incident energy, flux. So unit is the per unit time, or flux is nothing but the unit time per area. Okay, so this is the incident energy per second per area. This is the radiated energy per second per salt angle, and the ratio becomes the scattering per salt angle. So basically, if you take this bunch and divide that, you will obtain the scattering cross section per salt angle. Okay, that is the good wording, and that will be equal to E square MC square over 2 epsilon complex conjugate that epsilon 0 square. And this is related with the this is dimensionless, and here this whole stuff is related with the square of the classical electron radius. So basically E square over MC square as the order is nothing but the classical electron radius. Why they call classical electron radius? Because if you equate the MC square rest energy to the what? Self energy of the electron, that is E square over R. If you equate M square to the E square over R, and if you take the dimension R, that will be E square over MC square, and this is the scaling of the classical electron radius. So, and you have this stuff here, and you know that what is this? That is the scalar product between the incident polarization of the incident electromagnetic wave, that scattered electromagnetic wave. And we did this, and you did also in your lecture notes and in the examination also. We said that if the incident wave is propagating along N0, they have some polarization perpendicular to that, and let's say it's scattered along N, which is making N theta, and theta, so let's say this is in the XZ plane. So this is the summary which we did several weeks ago. So if it is scattered by theta, then this polarization vector is moved down as a what? A E1, and if it is scattered along the XZ plane, then the E2 will be the E2 epsilon 0. Epsilon 2 will be the epsilon 0. So probably you remember what we did. So we did this carefully, and we look at the scattering parallel to the scattering plane and perpendicular to the scattering plane. Scattering parallel to the scattering plane is making as what? E1 0 and epsilon 1 0, and epsilon 1 is making an angle theta, and the scalar product is cosine theta, but the perpendicular component, they are aligned along the y-axis. So if you look at the scalar product between the perpendicular component of the polarization before the scattering and after the scattering, they are aligned. Therefore, the cosine, the scalar product will be 1. So the bottom line is the following. So the scattering cross section per salt angle. So look at the lecture notes. we did several weeks ago. That will be 1 plus cosine square theta. So each of the polarizations has the weight 1 over 2, and that will be in that form. Actually, this was your exam question. So electromagnetic wave scattered from the electron, and you find that the electric dipole moment of the oscillating electron, and you come to this result. So if you integrate this through all solid angles, you will find that the total scattering cross section, so the angular integrations will give some contributions as pi or something like this. So the result, so do this integration trivial, you will obtain 8 pi over 3 e square over mc square square. So the number, so this is called as a Thomson scattering cross section, and it is play a very important role in radiation transfer in the cosmic background photons, making lots of scatterings in space, in galaxies, and so on. So they have the polarization, and the new satellites such as Planck satellite is built up by the European Space Agency, looking at the polarization measurements of the polarization of the cosmos or cosmic background radiation. So, and as you see that this is proportional to the square of the classical electron radius, and the number is 0.6 times 10 to the minus 24 centimeter square. And this is the, this whole stuff here is the order of classical electron radius, and this is the square. So basically, in Thomson scattering is important. It works well at low energies, at high energies, at which the momentum of the photon comparable with the MC. Then we have to work on with Compton scattering, not Thomson scattering. So this is the Thomson scattering correction section, Thomson scattering, and valid at low energies. So we see that the scattering of the electromagnetic wave from the free charge. Now we will study a different concept which is called radiative reaction force, and we will study that the radiation for the bounded charge to the molecules or atoms. So radiative reaction force so the idea is the following. If there's the acceleration, there should be external force. But if the charge is accelerating, there is a recoil force. So if you want to accelerate a charge, there is some resistance, like a bullet emitted from the gun. So it will have some recoil effect, some resistance. So what we have at hand, we have the nice formula, Larmor formula. What does it tell us? The total power, non-relativistically, emitted from the accelerated charge related with the square of the acceleration. This is Larmor formula and non-relativistic. And if there is some resistivity in some recoil, some braking force in the acceleration, so if we want the accelerated charge, there will be some recoil effect. So basically the form of the Newton's law could be written as m dot v. You apply an external force, but there is some force making recoiling that is called as a radiation reaction force. How we can find this? We have the emitted power. If I integrate this emitted power at time interval t, I can find that the work, energy. And that work should be equal to the work done by radiation reaction force. Okay, so basically the tool is very simple. If you want to find that the radiative reaction force, take the any displacement that becomes total work done by the radiative reaction force, and I know that that should be equal to time integral of the total emitted power, because the total time integral of the total emitted power is the energy, and that should be equal to negative of the total emitted power. So work done by the radiation in a given time interval, let's say t1 and t2, is equal to negative of the total radiation, total energy emitted by accelerated charge. So that will be equal to time integral of total emitted power 2 over 3 e square over c cube, and v dot square, we can write that the v dot square is the v dot scalar product by itself dt. So there is one important thing here. We have time intervals t1 to t2. For cyclotron radiation, if it is periodic, we can integrate for one full period. So we can integrate the right hand side using the integration by parts. So let's say du, so let's say v bar or whatever. So if you perform an integration by parts, this turns to be the following. We have the negative side, so that will be v bar times u, so that is equal to there's a minus sign here, that will be 2 over 3 e square c cube, and integral of this v dot, so v bar times integral of this v, yes, integral of this v dot dt will be v, and we have the v bar, that is v dot, from t1 to t2 minus, and multiplied with minus, if you multiply one more minus, plus 2 over 3 e square over c cube v double dot v integrated time 1 to time 2. So the tricky point here, at t2 and t1, both v and v dot, we require equal to 0, or they are equal. So either you can call that v are equal to 0, or you can call that at T1 and T2 the system is the same. This is valid in the periodic motions. So basically, we will ignore the first part, and then we can collect the left hand side and right hand side on the parentheses of v dt, and this turns to be from T1 to T2 if radiation reaction force minus 2 over 3, take this to the left hand side, E square over C cube, and we have the V double dot here. The interesting part here, we have the derivative of the acceleration, and if you take the common parenthesis of V dt, and this should be equal to 0 as overall. So all you do, you take this part to the left and take the V dt parenthesis. So if this is 0, then that means that the F radiative reaction force should be E square over C cube derivative of the acceleration. So what does this formula tell us and how it is used? So basically, we have acceleration is equal to external force plus radiation reactive force, and if we call that the F rad radiation reaction force multiply by m divide by m, this turns to be 2 over 3 E square over C cube, and divide to the m, and we have V double dot. So this is the force, this whole should be acceleration, this is the double dot, therefore this is equal to unit says the time, which is called tau, and this time is short. Tau is at the order of 10 to the minus 24 seconds. So as a feeling, 10 to the minus 24 seconds is the passage time of the light from the classical electron radius. It's very short and tiny, okay? And basically, you can write this as a m tau V double dot, and if you plug in here and take the left hand side, you will obtain m V dot minus tau V double dot is equal to external force. So this is a modification of the Newton's law. So basically, the situation is the following. I will do an example, but before going to do, there is one unlikely thing here. What happens if there is no external force? If you don't apply an external force, this formula tells you that two solutions. If external force is 0, this formula tells you that mass times acceleration minus tau times derivative of the acceleration have to be 0, and cancel this. Then you can find a solution for the acceleration. So how you can find the solution? This is the time derivative of the acceleration. This is the acceleration. It's a simple exponential integral. So you can obtain two solution. Acceleration could be 0 for a given initial condition, or some a0 e to the t over tau. So we are not happy this in the second one. A0 should be 0 if there is no external force, because that tells you that if there is no acceleration, this is accelerating. If there is no external force, if there is no external force, the charge is accelerating. So there is speculation of this. So it is called pre-acceleration. If you start to turn on the external force, the charge starts to accelerate at short time scale tau, because the exponential time scale here is the tau. Tau is the short. Short means that the tau is the time scale at which the light passage from the radius of the electron. So basically, we call this is an unlikely solution, let's say. So this is the good solution. Okay, if there's no external force, the things have to be 0. A should be 0. If there is no external force, A should be 0. So otherwise we have the problems. But if you let the external force, the system is working well. So then I will do the example of this, and that example will take maybe 20 minutes or 25 minutes. Then that will be the end of the course. So now let us write that the mass times acceleration, let's say in one dimension. Suppose that we have the spring harmonic oscillator. We have this nice radiation reaction force we learn now, and let us have the driving force. Driving force, I will apply this in the following problem. Instead of free charge, now we will have the bound charges, and incident electromagnetic wave is the driving force, and the charge is oscillating, but it has a spring because it is bounded to the molecules or atoms. Okay, and why it is radiating? It is making radiation reaction force. Okay, so everything is there now. So this is a very nice system. So this is a harmonic oscillator. So there's a charge, mass, while this is oscillating, and there's a radiation reaction force, and driving force we will see later, that will be the electromagnetic force, incident electromagnetic wave. So basically, for the spring force, you can write mass times omega 0 square is the natural frequency of the spring. For the radiative reaction force, I can write mass times tau x triple dot, not double, because V double dot means that the x triple dot. Let us leave the F driving alone now. So this is m x double dot. So now propose a simple solution. Suppose that x is oscillating at some amplitude, some frequency. It has a phase also. Suppose that x is an oscillating function, because driving force will be oscillating function. So we see one thing here, nice. If I take the triple derivative of this, which I will need it in this calculation, if you take the triple derivative of x, proposing solution, what you will obtain? First derivative is sine times omega, omega sine minus sine omega. Second one, cosine times omega square. So the triple derivative will be omega square times the first derivative. So instead of x triple, if you put this information, you will obtain very nice equation. So this is minus, take to the everything left, you will get m x double dot this term, take to the there mass times omega square tau x dot, and what else? Take this to the left, omega 0 square x is f driving. So what is this? Damped harmonic oscillating with the driving force, okay? So this is like a velocity, so radiative reaction force is damping the oscillation. So let us call this stuff as a gamma. Now, next thing will be the following. This is a damped harmonic oscillator, and it has the driving force, and driving force will be the electromagnetic wave. So I am trying to investigate what kind of radiation I can obtain if the incident electromagnetic wave scattered from the bound charges in the molecules and atoms. Previous in the Thomson scattering, that was free, but now they are bound, okay? In the previous case, we don't have this for the Thomson scattering. So what you do the same thing. F driving will be the charge in the molecule or atom, epsilon 0, the charge times the amplitude of the oscillating field, and cosine omega t. So let us take the driving force this. This is the incoming electromagnetic wave to the bound charges, molecules. So then what I am going to do, I can write this, instead of writing this E times epsilon 0 cosine omega t, I can write this E times E0 I minus omega t. I can use the complex numbers. That is better in solution. You can take the real at any time if you want. Instead of representing as a cosine omega t, express this e to the I omega t. And divide everything to the mass, then you will obtain x double dot gamma x dot omega 0 square x will be E over E0 over m minus I omega t. Since now x double dot x are complex numbers, and propose a solution x of t sum x0 e to the minus I omega t. If you propose this solution and plug in the above differential equation, you know this from the waves course. So if you plug in there, you will obtain x0. x0 is a complex number. So double derivative of this will be what? Minus I omega times minus I omega will be minus plus. I and I minus plus. This should be, is it minus? I omega square. The second one, we will have gamma I omega 1. And third one will be omega 0 square. So times e to the I omega t times x0. So maybe this is better. x0 times e to the minus I omega t. And that is equal to E0 over m, that term. So from here, we can find that the x0 will be what? E over m omega 0 square minus omega square minus I gamma omega and E0. So if this is x0, then the full solution will be what? Full solution will be x0 times minus I omega t. So you solve the x0 from here. Then you can write that the x of t, x0 minus I omega t, and x0 is over there, that is equal to E over m, is it omega 0 square minus omega square minus I gamma omega. This is x0 times E0, e to the minus I omega t, x of t. Okay, this is the x of t, time dependent. Now, suppose that in 3 dimension, this oscillation will take in the what? Along the direction of polarization of the incident wave, okay, in general. So you can write this as a complex vector in 3 dimension. Okay, you can do this in 3 dimension, not in the 1 dimension. You can include that the polarization of the incident wave. Okay, I did there for 1 dimension. You can do for 3 dimension. Then the oscillation will take place along which direction? Along the polarization of the incident wave, because the electric field is oscillating epsilon 0. Okay, we have to include the polarization. Polarization is important in scattering. Then you can take the derivative of this. So if you take the derivative of this, you will obtain the velocity. If you take the 1 more derivative, you will obtain the acceleration. If you take the double derivative of this, this will brings down 2 times minus I omega. You will obtain what? Acceleration will be minus I omega square. The rest is the same. E over m omega 0 square minus omega square minus I gamma omega E0. So let us take the E0 out. E0 epsilon 0 head e to the minus I omega t. And what we derive in the beginning of the force, if I know that the acceleration and the incident polarization, I can calculate that the power emitted per solid angle, then I can calculate the scattered cross-section per solid angle. Okay, the power emitted per solid angle for a accelerated charge, if there is a polarization, is equal to E square over 4 pi c cube epsilon complex conjugate. This is the polarization of the radiation, dot product acceleration of the charge. Okay, now what I am going to do, I will take here and plug in, and I will find that the scattering cross section per solid angle. And I want to do this more quickly and discuss about the results. So power emitted per solid angle will be what? I have to take this, put it there, and take the square. I will have the square of this that will be 4 e square m square, that will be e to the 4 m square. So, and this is oscillating in time. I should write the time average of this one cycle. Then the result will be the same as before with the same coefficients. C over 8 pi E0 square, E0 square over there, and that will be normalized C to the 4, therefore we have to see. Again, 4 is what, 8 is nothing but 2 times 4 due to the oscillating, the time average of the oscillating cycle. Then what I have, E square over m, C square to the square. This is E square is there. E to the 4th, sorry about this. I'll take the square of this, that is E square, there's a E square, that was E to the 4. And this is C cube is C over C to the 4th. And what else I have? M square here. And at the same time, this stuff here is related with the classical electron radius. The same, E square over M C square, okay? And the leftover term will be omega to the 4th power, this one. And if you take the square of this, you will obtain, you have to multiply this by complex conjugate, and you will obtain, this is divided by omega 0 square minus omega square plus gamma square omega square. So if you multiply this with the complex conjugate, and you will left with what? Epsilon complex conjugate at epsilon 0. Polarization before the scattering, that polarization after the scattering. Now, again, do the same thing. What is this? This is the energy density times the speed of light. That is the incident energy per area. And altogether, you can write again the scattering cross section per solid angle is E square over mc square of square omega to the 4 omega 0 square minus omega square of square plus gamma square omega square. So if you look at the, for all possible polarization states perpendicular and parallel to do, again you will have the 1 over 2 1 plus cosine square theta coming from here, and that's all. And what we learned this stuff, so you can take the integral of the scattering cross section per solid angle through the all solid angles, and you can find the result. So that should be something like 8 pi over 3. You can take the integral. And what we learned this, so this is carrying several important things. Is it okay? Cosine square theta, same thing as before. So I am not writing this epsilon 0 that epsilon complex conjugate. So we are saying the n0 x y z incident wave along the n0 and then scattered by n. This is theta. We have the incident polarizations as a epsilon 0 2 epsilon 1 0. Then after the scattering, this is the perpendicular polarization perpendicular to the plane. This is the polarization parallel to the plane. So it's shifted by amount of theta. Therefore, we have 1 cosine theta coming from the polarization parallel to the plane, and the 1 is the polarization perpendicular to the scattering plane. Doesn't change. So this is the same exercise we did several times. Okay. So you can take this integral through those all solid angles. And what we learn from here if you take this, you will have the number 8 pi over 3 or so on, similar to that. And the important thing here is the following. This is the frequency, this is the scattering cross section. The important thing is this. If the frequency of the incoming wave is at very low frequencies, what happens? These are not important, and that goes with the omega to the 4. So you know that the omega to the 4. The omega to the 4 is the part of the ray light scattering at low frequencies we studied. So we can call this as a ray light low. And when omega is equal to omega 0, that is the resonance case. The scattering cross section goes to maximum value at omega is equal to omega 0. So this is something like this. And when the frequency is much higher than omega 0, it saturates and goes somewhere here, and this is the plateau of what? When omega is much greater than omega 0, that is the place of the Thomson scattering. And the width of this related with gamma. Gamma is related with radiation reaction force. So it's related with the damping. So the gamma is what? Width is important wide when gamma is high. So width is not important. So if the width is 0, that should be goes as a delta function. There is sharp pike we expect. So this part is, I erase the equations, but for the damping equation we have the only, if you look at remember the equation, we have the double dot, single dot, and no dot. So dot is the single dot is the friction term, velocity related with the velocity that is related from the radiation reaction force. But you can include the quantum mechanical effects, and that will be proportional to with the velocity, or x dot again. So that is important. So if you include the quantum effects, so this part will be affected. And this is called, if you include the quantum effects, that will affect as a radiation damping, so that will affect this term gamma squared. In other words, gamma will be modified if you include the quantum effects. So the formula we have what? X double dot gamma x dot omega 0 square x f driving. So you can add a term which includes the quantum mechanical effects. So emitted absorbed radiation and emitted radiation, and only effect will be here. Okay, so this part will be affected, and basically if you include the quantum mechanical dissipation, so that will be called as a resonant fluorescence. That takes into account that the absorption of the photon and ray emission. So this is, if you're interested in, this is from your book, chapter 16, I think section 8. We are not include the quantum mechanical effects. We have only radiative reaction force. It is making a damping here. But if you include the quantum mechanical effects, that will be proportional to x dot. In other words, gamma will be replaced with another gamma prime. Okay? But this will be related, now that will be related with the radiation damping plus some other quantum mechanical effect. And this is very nice because at low frequency it explains the ray light scattering, and here is the resonance absorption and ray emission, and at high frequencies it behaves as a Thomson scattering cross section. So that's all of the course. The course is over.